I decided to have a very experimental talk, which is not so much actually about stability and lifetime, but it's about barriers and encapsulation. And I'm still a bit curious to see how you like it, because it will be very, very experimental, and it will be a lot about the calcium test. But we have done a lot of stuff on this topic in the last years, and I would like to share it with you, and I think you can learn something out of it. Okay, I'll start with a bit of advertisement. In Dresden, we have lots of partners who are working on barriers and encapsulation. These two Fraunhofer guys and us, and these guys here who are doing permeation measurement. But I don't want to bore you with that, so let's go to my talk. So as I have announced, I will talk about barrier, and I will also talk about encapsulation, and especially why these two things are not the same. So this might apply to all of you who are measuring devices outside or flexible for a long time. Suren is smiling, he knows that it's not the same. So sometimes you have a good barrier which is measured to give a good WVTR, water vapor transmission rate, but still it's not a very good encapsulation, because there might be some trouble on the way. And also I'll talk a bit about requirements. So that will be my talk. And as this is a quite long talk, I cannot spare you the basics, because I'm talking a lot about the calcium tests. So what we are doing is the electrical calcium tests. I mean, all of you probably know the calcium test. So you measure the water which comes into an encapsulated device or test by this reaction of calcium plus water to calcium hydroxide. Was invented at Philips a long time ago. And this stuff is metallic and conductive, and this is transparent and non-conductive, so you can measure the electrical resistance, the optical transmission, or a localized optical version. So you put the calcium on top of the barrier. The barrier has pinholes, and at the pinhole the calcium degrades, and you get a local image which you can monitor your pinholes. Okay, so we stick to the electrical one. If we do that, it looks like this. This is our layout. So here you can see the calcium in the middle. After a while it vanishes, and then it's done. And you measure the conductivity or the current over time, and it gives you a nice linear slope which is decreasing, and that slope is proportional to the WVTR, the water vapor transmission rate. Whenever you measure permeation or talk about barriers, you should always note that there's a temperature and a humidity attached to it. Okay, so this slope is very important, and one of our students, Hannes, he worried a lot that it might not be real linear for calcium layers, and actually he found that when you look with the AFM on the surface of your calcium, it does not degrade homogeneously, but it degrades, it forms spots. There's a nucleation, and then the calcium hydroxide grows around it. So if you have a differential AFM, you see these islands are growing. So something is corroding to the bottom. There's a thin film around 60 nanometers and then getting wider. But if we do a comparison, so we have done all methods in parallel. So this is the optical calcium test. And here you have one slope. This is the AFM, just averaging the surface area which is corroded, and it gives you a slope. And this is the electrical calcium test. So it's all the same device measured at the same time in situ with all three methods, and you see basically these three slopes are the same. This one is a different optical way to evaluate. So it's pretty valid, although it's a bit inhomogeneous. Okay, so the calcium test is always good for surprises. Let's have a look at our setup. This is what we are doing. We built a huge homemade setup. Which gives us, so we put the calcium test up here, and then the barrier is here. This is our substrate, and then we have a saturated salt solution below, which gives us a specified humidity, and we put them in groups into larger assemblies to give us certain temperature. This is maybe not as precise as you want to have it in a certified measurement, but it's good enough to give you a number, to give a relative comparisons. And what is really cool is that we can measure a number of different climates at the same time, so up to 60 samples, each with individual humidity, more or less, up to 5 temperatures, all at the same time, and we can have huge, what we call matrix investigations to study barrier models. About this, my colleague Frederick will talk on Tuesday with a short flash talk, and we'll have a poster, so you can visit him if you want to have more details on this. Okay, I will talk a bit why I like the calcium test so much. It's because it can measure in a device like Geometry the encapsulation, because you can basically, you have a barrier film, okay, the barrier has a barrier value, but when you use a calcium test, usually you put the calcium or the device on the glass, and then you laminate the barrier on top and measure. So that's a very device-like setting, or you can flip it around, and that's what we usually do. So you can imagine this is a device or a calcium test. And you can do many other things, so you can use thin film encapsulation, so you put your calcium below the thin encapsulation layer, or you use glass on the back. And of course, this influences what you are measuring. So you have a very flexible setup, but you have to be very careful because the measurement is always determined by the weakest part. If you don't have a good side encapsulation, or if you have like something like this and one barrier is much weaker than the other one, then you're measuring the weaker one and not the good one, which you might want to measure. This is all very nice, but it gives us a lot of trouble because this is what we usually do. We have the barrier on a polymer film, so you have a PET or PEN, and you have a very thin barrier layer, put the calcium test on top. And what the calcium does on water exposure is it expands. And this is in general not a big deal, because we have only 60 nanometers, it's not so much. But if you put the calcium test directly on the barrier, it will break the barrier, so you cannot measure something. Okay, kills the barrier. So we introduced a buffer layer here. So we have now polymer, in this case a ZTO barrier, thin film, then a C60 decoupling layer, and the calcium test on top. And what you can see here, there's a reference value for this type of barrier. And here's the C60 interlayer thickness. And you can see, in this case, without C60, a thick calcium layer has a much lower WVTR because it breaks up the barrier much faster than a thin calcium layer, and if you introduce the C60 as buffer layer, it works. So a thin layer is very sensible, and it needs to be protected. In this case, this is our layout, and again here, barrier, and then we have the C60 between the calcium and the barrier. And this is interesting, but of course we wanted to go for real barriers now. So we went for ALD, and with our collaborators at NAMLab and IHM, we had a look at alternating oxides, aluminum oxides, titanium oxide, nanolaminates, in this case 1 nanometer thick each, and then stacked. And we measured the barriers of these on a PET substrate. And you can see, okay, with increasing thickness, WVTR gets much better. This is on a planarized PEN substrate. And this is the calcium on the back of the barrier film. So we measure a barrier. Okay, so this works pretty nice. Not as good actually as we have expected. So probably even the substrate. PET is a difficult substrate for barriers, or also PN. Everything which is flexible is usually rough and is a challenge for a perfect layer. So, but it works, and now we wanted to put it as a flexible thin film encapsulation, because this is what we can measure with our calcium test, and this is what we need for a flexible device. So we put the laminate, in this case now it's 3 nanometer each layer, on top of our calcium test or device. And then we wanted to introduce alucone layers, MLD layers, in between for flexibility and decoupling of defects. So we have a different setup. So now we have here 48 nanometers of this nanolaminate. Then we insert a 12 nanometer alucone. We insert 2 12 nanometer alucone layers, and we insert 3 12 nanometer alucone layers. Okay. If we measure this, it looks pretty cool because, okay, we have a very poor barrier for no MLD layers, but for more MLD layers, the barrier goes down a lot. So 1 times 10 to the minus 5, that's already a pretty cool value, even at these conditions. So we thought, whoa, we didn't expect our idea to work that well. So we have amazing way up barrier, and probably the soft interlayer can decouple the defects. Okay, but then Freddy and Hannes, they had a short look on top of it, and you see this. So basically, these are the surfaces of these layers, and you can see the barrier breaks again. There's bubbles, delamination, cracks. Probably it's again the calcium which expands and kills your barrier. What you also see, that for the 3 layers of MLD, it looks pretty fine. It's still there. So there's a good barrier here and a poor barrier there. So we wanted to know what's the real barrier of these stacks. So we went back to our original configuration, just put the barrier on top of a planarized PEN foil and the calcium test on top. And there you can see the number of MLD layers doesn't make a difference. So this is around 2 times 2 to the power of -4, regardless of the number of MLD layers. These open dots are a different method, a laser spectroscopy-based permeation measurement. So, and they confirm basically it's the same type of barrier. Okay, it's a good barrier, but no influence of the MLD. So what's happening is probably that if you have the TFE type of encapsulation, so you have the calcium test down here, and you have the decoupling layer and the ALD layer, then the calcium breaks the barrier, even if there's a decoupling layer. Probably it's a delamination at the bottom part. And in this case, the MLD barriers perform much better, because probably they are able to mitigate the strain somehow. If you do it in the barrier film type measurement, so we have the polymer at the bottom, then the ALD barrier, then decoupling layer, calcium, and our back encapsulation, it looks like all barriers are equal. So the C60 layer can mitigate the strain, no problem. So the MLD does not improve the WVTR, but apparently it can mitigate the strain and increase the durability or the flexibility of the barrier, even if this is an indirect proof. Okay, but this is not all of it. There's even more trouble, and this is probably also interesting for you. So this is a nice graph of a calcium test I've shown you before. So you see over several dozens of hours a nice linear decrease of the conductance. And this is again the barrier on the planarized PPEN or the PPEN foil. So now if we do it in a thin film configuration, so we have the calcium below and try to encapsulate it, it does not even survive putting it into the measurement system. It just is alive for a few minutes at maximum. So the barrier fails within minutes. What's happening there? So if you have it that way, with the PET facing outwards, it's stable. And if you do it like this, with the aluminum oxide facing the atmosphere, it dies immediately. So we try to stabilize it, or we try to look at it at first. So this is AFM and XRR, and you can see AFM, after 1 day in ambient, the surface has changed a lot. So this is a 20 nanometer film, and it changes. So this is a probably serious issue. Also, with XRR, we could fit the density, and you can see that within minutes, the density drops a lot. So what's happening there? We don't know exactly, but probably this is a low temperature ALD layer, which is well known to have remaining carbon, and probably it's also not stoichiometric, so it's very likely to react with water and other things in ambient atmosphere. So we have trouble here. And now we want to protect it and check how we can protect it. So we wanted to try stronger ALD layers, and you can see, so this is the time to break down 20 nanometers of aluminum oxide and 10 nanometers of the ALD protection on top. Okay, not so great. Hafnium is better, alucone is better, titanium oxide gives you great improvement, but still it lives only for 1 hour. So you can start measuring, but it dies pretty fast. And this is a very thin, sensible barrier. Imagine that your electrode of your device is also a very thin, sensible barrier. So stuff like this happens to your electrode as well. Okay, so it's still marginal. It doesn't work. So we tried to use something more solid. And of course, we went to the polymer, because if we do it on a polymer film, it works. So try to put the polymer on top. And we tried different polymers, spin-coated Ormosur, fluoropolymer from 3M, standard photoresist, and we just laminated a PET foil on top. And you can see that PET foil on top is really cool. So all of this polymer stuff performs much better than the ALD top coatings. Also, they are much thicker, to be fair. But still, the time to breakdown is only 24 hours. Okay, but we can measure something. So actually, to laminate the thick PET on top solves all our problems. It greatly increases the stability of this. And this is what we do for all our measurements, since we have done this. In this case, the 24 hours, they are still caused because we do not have the decoupling layer of the C60 below. So if we add the decoupling layer and the PET on top, then this is stable. But that really shows how much you have to protect your barriers. Okay, and as we don't have the C60 here, probably we cannot separate the mechanical properties from the barrier protection. So especially for the thin ALD layers, they might perform a bit better, but still it's clear that you need some kind of protection on your thin film encapsulation. Otherwise, it will not stand ambient atmosphere. Another nice thing which we can do with our calcium test is actually put it into a device or replace the device with the calcium test, basically what I've shown in the beginning. So this is a nice study of Hannes, and here we have a standard solar cell. This solar cell is very stable. Intrinsically, it's good for several thousands of hours, up to 10,000 I think we have measured, and it's still okay. And we took the top layers with the aluminum electrode and the B-film below and a bit of C60 and put them on top of our calcium test. And this aluminum electrode is a barrier. It's a quite good barrier, actually. It's in around 10 to the minus 3, sometimes even 10 to the minus 4. It depends on your deposition conditions. So now we have this intrinsic barrier on top of both devices, and below we have the calcium test or we have the dyeing device. So we can correlate our calcium test to the solar cell. And we did this at several temperature conditions or climate conditions. And what you can see is that these devices die pretty quick. We've measured the T50 doses with a bit of different methods, and at all climates they basically agree that these cells have a T50 dose of around 20 milligrams per square meter, which is not much. It's very little, actually. Harald and Roland have verified that this degradation is dominated by pinholes, so it's really area loss. Probably you can regain that efficiency if you replace the aluminum electrode, like we've seen before. So it's that interface which dies. And what's remarkable is basically that this T50 dose is very similar to what was predicted originally or a long time ago in this paper in 2001 for OLEDs, where they assume that you have 5 nanometer of magnesium which corrode away. And I think they predict 64 milligrams for the whole layer. So this is not a lot, and it's probably just an interface or something very small which is dominant for this type of degradation. So probably it's aluminum. Okay, with that I would like to conclude. So the calcium test is a very powerful lab permeation test. I hope I could convince you of that. It has a few troubles, but it's device-like and we can have as high throughput. Bit special is that the calcium expansion is a serious issue for the thin film encapsulation measurements, especially in these cases. And what's interesting that the MLD can mitigate the stress a bit. Low temperature ALD, as it is needed for thin film encapsulation, because you cannot do a hot ALD process on top of your devices. So low temperature in our case was 100 degrees or 80 degrees between them. You have to protect it, put on a protective film. And we also do this for all our aluminum electrodes. It really improves your measurement results a lot if you put a piece of PET on top. And then these T50 doses of water are around 20 milligrams for this specific system. It's not true for all solar cells. There's some more stable stuff around. But for this intrinsic system and this aluminum interface, it's very sensible. So I hope I could convince you that barrier and encapsulation are not the same, and this is something that you might remember. So you have to make sure that you measure the right thing And keep in mind that these thin film barriers, these perfect layers, which you expect to have a barrier of 10 to the minus 5, 10 to the minus 6, are very sensible things. So you have to be very careful with them. With that, I would like to thank all the people who did the work and all the great people who contributed, and the organizers for inviting me. Thanks.
Thank you, Lars, for the talk. We have time for several questions, so please ask him.
Thanks, Lars, for a nice presentation. Could you maybe comment on the lateral permeation in your measurements? How do you distinguish between the two effects? And maybe in that perspective also comment on how would you study adhesives together with the barriers, if it's possible.
Yep. Okay, the lateral dimensions of our test are very small. We are, I think, 0.7, 0.8 square centimeters, something like this, so that's very small. And area is a big challenge. So this is probably, if we measure several samples and kick out the worst ones, we probably get an ideal barrier, which is the maximum you can achieve. If you want to scale up, like some people in industry, you probably, or also you at Riese, you get much worse values because you have all the defects in it. We probably can avoid them with a smaller measurement area. And your second question? About the adhesives. Adhesives, yeah. That's a big advantage of the calcium test, I think, because you measure the whole package. So in principle, you can measure the adhesive in different ways. So if you want to measure edge-on permeation, you can glue two glass slides together and then you see how it shrinks. But it's also different from the device because you probably want to have it as device-like as possible. So you want to use your barrier, which you want in your device, on both sides, and the adhesive which you have in the device. Because if you measure only the adhesive between glass, it might be different than it is on your barrier film, because the interfaces might dominate things. But you can, I think you can select like glass with glue and barrier with glue, and then you can try to extrapolate what is your problem. So it's flexible, but it's a lot of work.
Thank you for a nice talk. I don't know if you mentioned it before, but could you comment on the adhesive you used to encapsulate? What kind you used? And also, I forgot the second question, so...
Okay, so I'll answer the first one and maybe you will remember. Okay, the adhesive, we only use adhesive. So traditionally, for a very long time, we'll use glass-glass encapsulation with a UV hardening epoxy. And when we measure a barrier type configuration, so put the barrier film at the bottom and then put the glass on top, then we use this epoxy, the UV epoxy. If we go for the thin film application, which is much more interesting, then we do not use any adhesive. We just put glass or a barrier and then we encapsulate with the thin film.
Oh, okay. I remembered. Could you recommend the metal you use to measure the conductivity of your calcium, like aluminum or silver?
This is a very difficult question, actually. I would go for, we obviously go for aluminum, but aluminum is not perfect because you have a corrosion element between the calcium is very reactive, and basically everything you put on top is more noble. So you have a potential difference between those two and you will have interface degradation. And this is still something we are looking into. But with aluminum, so far it works best. We have some better ideas.
Okay, thank you.
If no other questions, we leave the floor to the next speaker.